Everyone, welcome to my YouTube channel. Today I'm solving Leetcode question, all ancestors of a node in a directed acyclic graph. You are given a positive integer n representing the number of nodes of a directed acyclic graph, diag. The nodes are numbered from 0 to n-1 inclusive. You are also given a 2D integer array edges, where edges I equals from I to I denotes that there is on unidirectional edge from I to I in the graph. Return a list answer where answer I is the list of ancestors of the ith node sorting in ascending order. A node U is an ancestor of another node V if U can reach V via a set of edges. So first, this problem introduces a concept called directed acyclic graph, diag. So according to the definition, the graph is directed and acyclic, which means there is no cycle in this graph. So diag is actually a pretty, I would say, common and popular concept in graph. And then one of the application is Airbnb Airflow. I'm not sure if you have heard about that, but that's kind of also a utilizing the directed acyclic graph. So let's try to understand the problem a little bit better by taking a look at the example. In the first example, so there are like n equals to 8, edge list equals to 0, 3, 0, 4. So there's edge list. So for the node 0, 1, 2, so there is no ancestors. So you can only see the edges that's from 0 to other nodes, from 1 to other nodes, from 2 other nodes. There is no incoming edges into these nodes. So that's why in the output, their ancestors are empty list. For the node 3, the node 3 has 2 incoming edges, and then the ancestors are 0 and 1. And because 0 and 1, they do not have ancestors. So that's why for node 3, it only has 2 ancestors, 0 and 1. Similar for node 4, the ancestor is 0 and 2. For node 5, the ancestor is 0, 1, 2, 3. So there's one incoming edges to node 5. That's from node 3 to node 5. So in that case, we know node 3 is an ancestor of node 5. However, for node 3, it has 2 ancestors, 0 and 1. So in that case, based on our definition of ancestor, a node U is an ancestor of another node V if U can reach V via a set of edges. So in that case, 3 is 5's parent, so you can reach 5 from 3 directly. And then 0 and 1, they are like node 3's ancestors. You can reach 3 from node 0 or from node 1. So in that case, you can reach node 5 from node 0 and node 1. So first from 0 travel to node 3, and then from node 3 to node 5. So that's why for node 5, the ancestor is 0, 1, 3. So for node 6, the ancestor is 3, 4. And then for 3, 4, their ancestor is 0, 1, 2. So in that case, for node 6, the ancestors are 0, 1, 2, 3, 4. So how to solve this one? So it's also utilizing the topological sorting. So why we are sorting this one why we are solving this one utilizing topological sorting? So you need to find some where to start. So we want to start from the node that does not have any ancestors, if there is any. So for those nodes that do not have any ancestors, we start and find the nodes that directly connected to those nodes. So let's say we start from node 0, 1, 2, and then those nodes are they do not have any ancestors. So we know that in the result, their ancestor are empty list. And then from there, we're trying to find the nodes that we directly connect to these nodes. So that's the node 3 and 4. So when we look at node 3, we can reach node 3, and then from node 3, we go back and then check all the ancestors. Okay, from node 3, we know that the node directly connected to node 3 is 0 and 1. And then in that case, since we already considered and find the ancestors for node 0 and 1, in that case, we just append or add the ancestors of node 0 and 1 to the ancestor list of node 3. So in this case, node 0 and 1 does not have any ancestors, so node 3, the ancestor of node 3 is just 0 and 1. But let's take a look at another example. Let's say in this case for node 6, so utilizing this logic, we first find, okay, from node 3, we can reach node 6, and then we add 3 to the ancestor list of node 6. And then we take a look at node 3. So before we reach or consider the node 6, we already covered the node 3 utilizing topological sorting. Okay, so in that case, we already have a list of ancestors for node 3. So in that case, we just add all the ancestors for node 3 to the ancestor of node 6. And then similarly, we can reach node 6 from node 4. So we add node 4 to node 6 ancestor list. And then we also add all the ancestors of node 4 to the ancestor list of node 6. So that's kind of how we find all the ancestors. So we start from the nodes that without any ancestor, that starting point. And then we reach the next nodes, the nodes directly connect to those nodes. And then after we cover those nodes, I find their ancestors, we reach to the next level. So that's kind of how we find the ancestors for each node. So let's write the code. So in this case, let's try utilize the adjacency list. So import from collections. And then we also want to check the integrates. Let me see. Yeah, we are trying to check the integrates. For parent and child in edges. So now we are constructing this adjacency list. So basic adjacency list parent equals dot append child. So basically for this adjacency list, it's a list. The key is the parent node, and then the value is the child node. Parent node means like, okay, 0. For 0, all the node it can reach from node 0 is node 3 and node 4. So in this case, in this adjacency list, the key is 0, and then the value is the list containing 3 and 4. So you can see there are like two edges, direct edges from 0 to 3 and 4. And then integrate child. So it keeps track of how many parent nodes a child node has. Let's say in this case, we will check, okay, the when we are checking the parent equals 0, child equals 3. So in that case, we know 3 has a incoming edges. So the integrate is from 0 to 3. So that's why we increase by 1. And then when we are looking at the pair 1, 3, we increase the incoming edges for 3 by 1 again. And then after that, we are trying to find the starting point. So from collections, import dq. So q equals dq. So node for node in range n, if node not in degree. So this Q contains the all the nodes that so at the very beginning, this Q contains all the nodes without any incoming edges, which means all the nodes without the ancestor. And then as we are visiting the nodes, we put the node into the queue only if we have already visit or find of its ancestors. So we also want to keep track of the results. So while q node equals q dot top left, and then for child in no adjacency list node result child the add node and result child the update result. Okay, so let me explain what the code does up until this point. So we create a result in order to keep track of the all the ancestors for each node. So since we the node is denoted by the nodes are numbered from 0 to n-1. So in that case, we utilize an index to indicate the nodes, and then result I is the ancestors for node I. And then we check the queue. We pop a node from queue. So and then in that case, after we pop the node, we check all the child. So let's say in this example, when we pop up 0, we check the child 3 and 4. And then for each child, so we add this node to the ancestors. And then after that, so this line is, okay, we not only add a node, the direct parents to its ancestor list, we also want to add all the ancestors of that parent to this child's ancestors. So that's what the line 24 does. So let's take a look at an example. Let's say if we are checking, let's say in this case, if our node is node 3, and then node 3, the child is node 5, right? And then in that case, you add node 3 to node 5's ancestors. That's what the line 23 does. And then after that, 0 and 1, they are both ancestors of the node 5 as well. And then remember, by this point, we already add 0 and 1 to node 3's ancestors. So in that case, we just put the node 3's ancestors that's already stored in the result, and then add them to this node 5's ancestors. So the reason why I'm utilizing a set here instead of utilizing a list is because like there could be duplicates. Let's say for this example, for node 6, node 6 had two direct parents, node 3 and 4. Node 3's ancestors are node 0 and 1. Node 4's ancestors are node 0 and 2. So node 3 and node 4, they have a common ancestor, node 0. So if I just simply utilize a list instead of set, and then list append, the 0 would appear twice. But here, when I utilize the set, so there's no duplicates. So for those who are not very familiar with the set, you can view the operation add similar to how you do the append for the list. And then this update is kind of similar to how you do extend for the list. But in this case, it ensures there is no duplicates. After that, so let's try to update the integrate. If integrate child is 0 after update, which means we have already covered all the ancestors for that child. We append that to the queue. And then in the end, we need to return the result, the list of ancestors of the eth node sorted in ascending order. So in that case, we return sorted. Okay, so that's the end of this video. We are finding all the ancestors of a node in a diag utilizing the topology sorting. If you subscribe to my YouTube channel and then check my earlier videos on the course schedule too, you will see that the entire methodology or the framework for solving these two questions are very, very similar. That's because they are all solved utilizing the topological sorting. If you liked my video, please feel free to subscribe to my YouTube channel. Thank you.